Yeah. Good evening, students. Today we are going to discuss synchronous generator in gate point of view. So synchronous generators in gate point of view. So we are going to be discuss now. So see here, synchronous generator construction. In synchronous generator construction, there are two types of synchronous generators. There are two types of synchronous generator mainly: silent pole rotor construction, cylindrical rotor construction. One is cylindrical rotor construction. So here, what is the differences between in silent pole rotor construction and cylindrical rotor construction? See, these are the two rotor constructions. Stator is similar to this. Both either may be cylindrical rotor synchronous generator and silent pole rotor synchronous generator. The stator construction is same for the both the generators. But coming into rotor construction, there are two types of generators. One is silent pole synchronous generator, another one is cylindrical rotor synchronous generator. See here, the rotor itself is cylindrical in shape, round shape. So that's why we are going to be say that these generators are nothing but cylindrical. While seeing silent pole, the poles are projected on rotor surface of the generator. So those generators are nothing but silent pole generators. See here, there is a small differences between these two. So in this case, 1/3 slots is 1/3 area is left to made slots to form the field poles. When we are going to be taking here, so remaining part 2/3 we are going to be made some slots to accommodate the field winding. In synchronous generator, the field winding is placed on the rotor winding and the armature winding is placed on the stator winding. So why? Because here we are going to be generate more electrical energy because more number of conductors are required to generate the more electrical energy. So for that reason, it is not possible to driven the rotor at higher speeds to obtain the generated voltage as a maximum. So here, see here, Eg is equal to, already we know that basic equation pi and n. So here we are going to be generate the electrical energy based on speed and as well as flux. So when we are going to be run the generator, if the rotor is having high inertia, it is not possible to driven at a higher speeds. So for that reason here, the field winding is placed on the rotor and armature winding is placed on the stator. In a case of DC machines, here the synchronous generator windings are opposite. So when we are going to be placed as an 1/3 is left to 1/3 area is left to form the field poles and 3/3 is placed as an slots, accommodation slots to place as in a field winding. When this field winding is excited, there will be north and south poles are developed on the rotor. When this rotor is going to be driven at some synchronous speed, so this rotor flux is cut the stator conductors and EMF will be introduced in the stator conductors. That is the actual principle of our generator. So this is a rotor construction. While coming into silent pole synchronous generator, the poles are mounted physically. The poles are mounted on the rotor surface. These poles are projected in nature. When these poles are projected in nature, because of this projecting field poles, the air gap between the rotor and stator is non-uniform. In a case of silent pole generator, the area between the along the poles is, so suppose when we are going to be made here outer surface is it is a stator for that. So here we see this is an axis. So here area is less. When we are going to see here automatically how it is an air gap is more. So there is a non-uniform of air gap between the rotor and stator in a case of silent pole synchronous generator. While coming into cylindrical rotor synchronous generator, the air gap is uniform. When this air gap is uniform, flux distribution is uniform. The generated voltage also uniform in a case of cylindrical rotor synchronous generator. While coming into silent pole generator, the air gap is non-uniform because of projecting force in the rotor. The air gap is non-uniform. Flux distribution also non-uniform. The generated voltage also non-uniform in a case of and cylindrical. So coming to armature winding. So here the armature windings are classified into two types mainly. One is concentrated winding, another one is distributed winding, and also short pitched winding and full pitched winding. So while taking here is in generally synchronous generator harmonic as in a distributed winding. So similarly, distributed winding and also that winding is full pitched winding, and short pitched winding. Generally, instead of full pitched winding and short pitched winding, what is meant by the full pitched winding? What is meant by the short pitched winding is full pitch 180 degree. The winding is if the winding is short pitched, how do you say that the winding is short pitched in the sense the distance between the two coils at a coil is less than 180 degrees, then the winding is nothing but short pitched winding. So generally in a case of short pitched winding, elimination of higher order harmonics. There is a elimination of higher order harmonics. See here, there is a short pitch, providing as in a short pitched winding. The induced EMF ER is equal to 2E cos alpha by 2. 2E, the resultant EMF induced in the coil is ER is equal to 2E cos alpha by 2. So because of this formula, we are going to understand. So then the full pitched winding is 2E. The ratio of these two, pitch factor is nothing but ratio of when the winding is short pitch, when the winding is short pitched to winding is full pitched. So for that reason, we are going to be obtain Kc pitch factor Kc is equal to cos alpha by 2. Cos alpha by 2. So when cos alpha by 2, here when we are going to be taken as a cos alpha by 2. So because of this pitch factor, the winding we are going to be designed as an asynchronous generator is always less than 180 degree. By providing is less than 180 degree, so we are going to be eliminate the dominating harmonics. While see here distribution factor, the formula for the distribution factor. Kd equal to sine m beta by 2 by m sine beta by 2. So distribution factor formula. So here distribution, by using this formula, we are going to be eliminate the all higher order harmonics. All higher order harmonics. Suppose if Kc equal to 1, then it is nothing but full pitched winding. If Kd equal to 1, then the winding is nothing but concentrated winding. These are the two important questions in a case of gate point of view. So this is the induced EMF per phase, that is nothing but 4.44 Kc Kd F flux per pole and turns per phase. See here EMF equation already equation. EMF equation of alternator is, we are going to derive that one. So that is nothing but 4.44 pi f turns per phase multiplied with Kp and Kd. Harmonics in generated EMF. Here, what are the harmonics? The multiples of fundamental frequency is nothing but as a harmonics in generated EMF. So generally these harmonics are more in a case of silent pole synchronous motion rather than cylindrical rotor synchronous motion. Why? Because in cylindrical rotor synchronous motion, the air gap is uniform. Because this air gap is uniform, the flux distribution also uniform. The generated voltage also uniform. While coming into silent pole synchronous generator, the air gap between the rotor and stator is non-uniform. Flux distribution is non-uniform. The generated voltage also non-uniform. See here, there are some types of harmonics. Generally, there are some types of harmonics. What are the types of harmonics? Means space harmonics and slot harmonics. So these are the slot harmonics. By providing the uh, slots on rotor and stator periphery, there will be slot harmonics are developed. So how we are going to be reduce this slot harmonics is by skewing the rotor slots only. So see here, elimination of harmonics. By using distributed winding, all higher order harmonics are eliminated. By using fractional slot winding, all dominating harmonics are eliminated. By using fractional slot winding also, we are going to be reduces the higher order harmonics. By using skewing the rotor, eliminate the slot harmonics. So these are the elimination of harmonics in a case of synchronous generator. Next, armature reaction. Already we know that what is meant by the armature reaction. Already the same armature reaction we are going to be studied in a case of DC machine also. When the generator is loaded, there is a generated voltage drive current through the load. The same current is flows through the armature winding. Then there will be a creation of armature flux. So here, when we are going to be connected, so loads here based on the type of the load, there will be armature reaction is takes place. If the type of load is going to be resistive load, there will be cross magnetization effect. If the type of load is going to be inductive load, there is a demagnetization effect. If the type of load is going to be capacitive load, there is a magnetization effect. These are the effects for armature reaction. One is cross magnetization effect, demagnetization effect, and magnetization effect. See here, when we are going to be taking when armature reaction at unity power factor load. Unity power factor load means when we are going to be connected resistive load to the alternator. See here, I am drawing as an alternator, symbolic representation of alternator. It is in a rotor generally. Rotor is connected to prime mover and runs at rated speed. By giving field current to the field winding, the generator is going to be by giving a rated field current to the field winding, then the generator build up rated voltage here across the armature terminals. When load is connected, when load is connected, so because of this load, there is a load current starts flowing through this armature winding. That because of this, there will be a flux is created. That is flux, main armature flux. Already in field, because of this field winding, there is a main field flux. So here, see here how the armature flux and main field flux. When we are going to be connected, see here, unity power factor load. So here I phase is in phase, E phase is in phase with IA. Then flux also in phase with here. So means automatically the armature flux crosses the main field flux. This is the main field flux. The armature flux crosses the main field flux. Then it is called as a cross magnetization effect. So because of this cross magnetization effect, the main field flux is going to be distortional. The generated voltage also distortional. So next is coming to here armature reaction at zero power factor load. Where will be taking as in a zero power factor load means a pure inductive load or pure capacity load. Here lagging load means inductive load. Already we know this. See here, suppose now see here. So here main field flux because of field winding is excited, the field current because of the field current flowing through the field winding, there is a main field flux is produced. Because of this main field flux cut by the stator conductors and EMF will be induced. These stator conductors are pure inductive nature. So for that, so E phase is lags main field flux by 90 degrees. When here we are going to be connected as a pure inductive load. This individual voltage drive current through the load, but here load is pure inductive load. Automatically, the IA phase current is lags E phase by 90 degrees. Means suppose it is in a flux, the flux vector lags by E phase by 90. Here it is in a 90. It is in a flux vector. Now, so when load is connected, pure inductive load, this E phase again, the IA current is starts flowing through the armature terminals. Because of pure inductive nature, this lag, E voltage by flux 90 degrees again. So means here phi A flux and main field flux both are opposite direction. This one will be like in this direction. Here it is in opposite direction. Because of this opposite direction, there will be a demagnetization effect takes place in the alternator. Because of this demagnetization effect, the generated voltage is reduced. The generated voltage is going to be reduced at low terminals. To maintain the low terminal as before as in a constant, we are going to be increase the excitation of the alternator. So for that reason, we are going to be say that when the generator is operated under pure inductive loads, the generator is going to be operated over excited condition. Why here over excited means here because of demagnetization effect, the generated voltage is reduces. To maintain the rated terminal voltage, here we are going to be increase the field current such that we are going to be increase the excitation of the field current. For that reason, we are going to say that the generator is connected to pure inductive load. The generator is going to be operated under over-excited condition. Over-excited condition. It is a very, very important question for the gate point of view. They are going to be asked the question. So when we are going to be connected pure inductive load to the generator is going to be operated over-excitation, under-excitation, and normal excitation. So that is the questions. So next, coming into pure armature reaction is connected at zero power factor leading load. Leading means capacity load only. So zero power factor means pure capacity load. When pure capacity load is connected, means automatically the main field flux, because of field current excited by the field winding, there is a production of main field flux. This flux is a useful flux, our working flux, our required flux. Because of this flux cut by the stator conductors, and EMF will be induced in the stator. So that individual EMF E phase lag phi m by 90 degree because of pure inductive nature. Lag 90 degree. So when pure capacity load connected across the load terminals, armature terminals, then this E phase voltage is drive current to the load. This current is going to be again lead E phase by 90 degree. Lead E phase by 90 degree means automatically the phi A flux in phase with main field flux. Both fluxes are same direction. See here, both fluxes are same direction. When both fluxes are same direction, the resultant flux developed in the air gap is maximum. Increases. There is a magnetization effect here. So because of this, both fluxes are same direction. The armature flux is going to be added to the main field flux such that we can say that there is a magnetization effect. Because of this magnetization effect, the load voltage or terminal voltage of the alternator is going to be increases more than the rated voltage. When it is generated more than the rated voltage, so here we are going to be reduce the excitation of the alternator to produce the rated terminal voltage across its load terminals. Because of this, the generator is connected to pure capacity load. The generator is going to be operated under excitation condition. Why here is an under excitation means here because of magnetization effect, the main field flux added to the armature flux, resultant flux is going to be increases. The generated voltage also increases. When generated voltage increases means the terminal voltage also increases more than rated voltage. So to maintain the rated terminal voltage here, the excitation of the alternator is going to be reduces. The excitation of the alternator is going to be decreases to maintain the rated terminal voltage of the alternator. Such that we can say that when the machine is connected to pure capacity load, the machine is going to be operated, the generator is going to be operated under excitation. There is a concept here for synchronous generator: under excitation, over excitation, normal excitation. When the normal excitation takes place, in the sense when unity power factor loads are connected to the synchronous generator. When the over excitation takes place means when we are going to be connected, pure inductive loads are connected to the armature terminals of the alternator. Similarly, under excitation. Under excitation means pure capacity loads are connected. These are the very, very important questions for the gate point of view. Next, coming into synchronous reactance. So, what is meant by the synchronous reactance? So, generally, here there is a fictivity reactance and XA and leakage reactance XL. This combination of fictivity reactance, that is nothing but armature reactance XA plus XL leakage reactance, we can say that synchronous reactance XS in synchronous generator. So actually what is meant by this reactances means, so here because of armature reaction is existence, there will be a demagnetization effect. So to model the armature reactance, we are going to be taken one term. The term is nothing but XA, armature reactance. When armature flux is close to the armature winding, there will be some amount of flux is going to be linked with only armature current. Because of that flux, an EMF will be induced in the armature conductor. This induced EMF opposes the main induced voltage. So because of that, there will be some voltage drops takes place in the alternator. That voltage drop is nothing but I into XL drop. Here I into XA drop. So this is regarding synchronous reactance in synchronous machine. See here. Next, load characteristics. So before we enter into the load characteristics, so we are going to be studying a voltage regulation of the alternator. See here, voltage regulation, very important concept for the gate point of view. So voltage regulation. So what is meant by the voltage regulation means it is the ratio of here ratio. What is the ratio? This is the ratio. No load voltage to full load voltage to rated voltage. It is the ratio of change in terminal voltage to. It is the ratio of change in terminal voltage to rated terminal voltage is nothing but voltage regulation when load is suddenly thrown off with the same excitation and same speed. What is the definition of voltage regulation means? It is defined as the change in terminal voltage to rated terminal voltage. Here above is the E minus V is a change in terminal voltage to rated voltage. V is a rated voltage, E is a no load voltage. So here what is meant by the voltage regulation of the alternator means here from change in terminal voltage from no load to rated voltage by ratio of rated voltage. So see here. So how we are going to be calculate the voltage regulation? In a case of there are two methods are required. Two different methods are required in a case of synchronous generators. So what are these two different methods in a sense? In a case of silent pole synchronous generator, to evaluate the voltage regulation, we are going to be taken as a bondage two reaction theory. Bondage two reaction theory. By using this bondage two reaction theory, we are going to find out the voltage regulation of silent pole synchronous generator. So while coming into cylindrical rotor synchronous generator, there will be some voltage regulation methods. Those methods are nothing but EMF method, MMF method, ZPF method, ASA method. ASA method. These are the methods. So why here? See here, what is the differences between silent pole synchronous generator and silent pole synchronous generator and cylindrical rotor synchronous generator? Already we have discussed this point. In silent pole synchronous generator, the air gap between the rotor and stator is non-uniform. Along the poles is minimum, in between the poles is maximum. So that single reactance is not sufficient to model the armature reaction. So for that reason, we go for a two reactance model, that is nothing but two reaction theory by founded by Bond's two reaction theory. So while in a case of cylindrical rotor synchronous generator, the air gap between the rotor and stator is uniform. So for that single reactance is sufficient to model the armature reaction, that is XA only. So this is the reactance to model the armature reaction to find out the voltage regulation in a case of cylindrical rotor synchronous method. So actually there are different types of methods, mainly voltage regulation methods. One is the direct method, another one is the indirect method. So direct method is, it is only for low rating missions it is applicable. Means simply, see here, suppose it is an alternator diagram. See here, it is in a rotor circuit. This one is rotor. So it is in a stator circuit. One is in a rotor circuit and stator circuit. Symbolic representation of alternator. So see here, direct method, how we are going to be measure the voltage regulation by using direct method means simply the alternator is going to be runs at rated speed. We are going to run the rotor at rated speed. Then we are going to be excited this field winding by giving as a DC supply. Then this field current is adjusted, the generated build up rated voltage across its armature terminals, VT by connecting as a load. By connecting as a load here. By connecting as a load, we are going to measure this VT value. Then automatically, so with same excitation, same speed, the load is disconnected. Then we are going to measure the voltmeter reading. So before initially, first of all, we are going to run the generator at rated speed by using primary input. Then by adjusting the DC supply to the field winding, we are going to be produce the rated voltage across its armature terminals. When we are going to place as a load, when this load is reaches to rated condition, automatically this voltmeter read as a rated voltage. Then suddenly we are going to be removing the load by the same excitation and same speed. Then this voltmeter is measured, no load voltage, that is nothing but E0 voltage. Under load condition, VT voltage is measured. That directly E0 minus VT by VT will give as a voltage regulation of the alternator under load condition by using direct method. But this method is not possible high ratings of the missions. Why it is not possible to provide in laboratory? Simply this direct method is conducted in our laboratory, practical laboratory. But while coming into indirect methods, these indirect methods are suitable for high rating mission. So in this method, we cannot place the directly load on the mission. Simply by conducting this test by some characteristics, we are going to be evaluate the voltage regulation of the alternator. EMF method or synchronous impedance method, first method. Emf method, ampere turns method. ZPF method, or Portier triangle method. ASA method, American Standards Association method. MMF method, ampere turns method. These are the four important methods to calculate the voltage regulation of the alternator. Apart from this, which method is gives as an accurate results is, that is nothing but ZPF method. ZPF method is the will gives as a more accurate voltage regulation when compared to EMF method and the MMF method. In EMF method, voltage regulation will obtained as more than the actual value. by conducting voltage regulation, by conducting to find out the voltage regulation by using EMF method. In this EMF method, the voltage regulation we can obtain more than the actual value. More than the actual value. For that reason, this method we can call as a poor method or bad method. Poor method or bad method or pessimistic method. There is a one name for this one. This method we can call as a pessimistic method. So ampere turns method, MMF method. In this method, the voltage regulation is obtained less than the actual value. That's why this method we can call as an optimistic method. Optimistic method. While coming into EMF method, the voltage regulation obtained in this method is nearer to the actual value. That's why this method will give us an accurate results when compared to all other methods. All other methods. See here, first method, EMF method. What is the test to conduct to find out the EMF method means OC test and SC test. And also we require armature resistance also. So means what are the tests required to find out the voltage regulation by using EMF method means OC test and SC test, armature resistance test. See here, open circuit test. Here armature terminals are open circuited by connecting as a voltmeter. So then here we are going to be run the alternator by giving as a prime mover input at rated speed. Then we are going to be given as a DC supply by adjusting the DC supply for the field winding. The current flows through the field winding is measured by as an ammeter and the generated voltage is measured as a voltmeter VT. From that we are going to be plot as in a graph field current versus terminal voltage. So here field current is 0. The generator runs at rated speed. If the field current is 0, the generated voltage is 0. The voltmeter reads as in 0. Now slowly we are going to increase the field current from 0 onwards. The field current increases, the generated voltage also increases. Like that we are going to increase the field current, the generator build up. So 5 to 10% more than its rated voltage. At each step, we are going to be recorded field current versus terminal voltage. From that, we are going to be plot as in a graph. That graph is nothing but OCC curve. Is an x-axis we are going to take as field current, on y-axis we are going to take as a terminal voltage. From that, we are going to be drawn as an OCC curve, open circuit characteristics. Next, short circuit current, short circuit test. So in this test, initially we are going to be set the field current of the alternator is 0. Then we are going to be short circuited the armature terminals by an ammeter, short circuited armature terminals and by ammeter. Then short circuited armature terminals and an ammeter. Then by adjusting the first initially we are going to run the speed of the alternator rated speed, then field current is set to be 0. Then by short circuited the armature terminals by using the ammeter. Then slowly increase the field current from 0 onwards. Then when it reads as an ammeter is in a rated value, then we are going to be take the readings of field current versus armature current or short circuited current. So from that we are going to be drawn as a graph field current versus armature current. That characteristics are nothing but short circuit characteristics. So generally these characteristics are linear characteristics. There is a question from the gate point of view. Why these short circuit characteristics are linear in the sense, here when we are going to be short circuited armature terminals of the alternator, a small field current is a fractional field current is required to flow the rated current through the short circuited terminals. So for that reason, the field current versus armature current characteristics are linear characteristics. Linear characteristics. And this test, the machine will be acting as an purely inductive load connected to the alternator. That is nothing but in this case, there will be a demagnetization effect. Next, see the calculation of voltage regulation from EMF method. For that reason, so we need to follow some steps. What are those steps in the sense? The SCC characteristics and OCC characteristics are drawn same graph sheet. Then at any particular value of field current, that will be projected to the SCC and OCC. When it touches SCC, that will be drawn with respect to y-axis will give us as in a short circuited current, and that the projected line will touches as an OCC, that will be given as an EOC, open circuited voltage. Simply, the synchronous impedance is nothing but open circuited voltage by short circuited. So especially in this test, we are going to be find out the synchronous impedance. For that reason, this method also called as a synchronous impedance method. Synchronous impedance. Why it is called as a synchronous impedance method means, so by measuring the synchronous impedance from this graph sheet, we are going to be obtain the voltage regulation of the alternator. So see here, below the saturation point of the OCC curve, we are going to be taken as at any particular value of field current that will be projected to SCC and OCC. Again, it will be drawn to the y-axis. So if the curve will be, see here, the OCC curve projected to VOC line, and the SCC will be projected to ISC line. So then ZS equal to EOC by ISC at any particular value of field current. Once we got the ZS, by using the stator resistance method, already we are measured as a resistance, then XS is equal to square root of ZS square minus RA square. Z square minus RA square. Once we got the XS value, synchronous reactance, then by using this formula, V phase cos pi plus IRA whole square plus V phase sin pi IA, not XS here, XS whole square. So plus or minus, here plus or minus we are going to take in plus for lagging load, minus for leading load. So already we know that rated voltage, we know that power factor, rated current of the alternator also we know. By conducting the stator resistance test, we measure as an armature resistance. Simply by conducting OC and SC test, by plotting the OC SC characteristics or same graph sheet, at any particular value of at any particular field current will gives as in EOC and ISC. From that we are going to be calculated ZS. Once we know the ZS, we are going to find out the XS. Then substitute here XS value. We are going to be obtain no load voltage. Already we know the rated voltage. This is V as a rated voltage. Then by using this no load voltage is measured, then we are going to obtain the voltage regulation of the alternator. Generally, in this method, we are going to be measured the synchronous impedance unsaturated zone. When it is measured unsaturated zone, the synchronous impedance is more unsaturated zone when compared to saturated zone. So for this reason, in this method, the voltage regulation is obtained more than the actual value. That's why this method we can call as a pessimistic method. See here, in this method, we are going to be measured the synchronous impedance unsaturated zone. Unsaturation synchronous impedance is greater than the saturation impedance, synchronous impedance. This is the important gate point of view question. The another name for EMF method, pessimistic method. Next method, EMF method. EMF method also same. Similarly, to find out the voltage regulation by using EMF method, following tests are required: OC test and SC test and armature resistance test. See here, it will be different when compared to EMF method. Why this is an ampere turns method in the sense, by using flux vectors, by knowing the fluxes, armature fluxes and field fluxes and total fluxes, we are going to be obtain the voltage regulation in this method. A simple here first in this, by conducting OC test, what we are going to be measured in the sense. So the synchronous generator is runs at rated speed by using primary input, and field current is adjusted such that there will be a rated voltage build up in open circuited of armature terminals. That field current is measured. That field current is main field current IFM. By conducting short circuit test, so again the alternator is runs at rated speed by short circuiting the armature terminals. Now the field current is adjusted till rated currents are flows through the armature winding. Then we are going to measure the field current. What is this field current? IFA is the main field current required to flow rated current through the armature terminals. What is meant by the IFM? It is also main field current required to produce rated voltage its open circuit terminals. Then vector sum of this IFA and IFM will give us as an IFT. Because of this IFT, when measured an IFT on x-axis, that value will be projected to OCC. That again that will be drawn with respect to horizontal. It will be touches voltage axis. That voltage will give us as a no load voltage of the alternator. So this no load voltage of the alternator in this test we are going to simply finding as a from the graph sheet. See here some methods, some calculation steps. So what is the step? First step, see here, the open circuit characteristic and short circuit characteristics are drawn same curve sheet. Then the field current IFM to give rated voltage E obtained from the OCC characteristics. Already I told you this. Next, similarly, same. The field current IFA is to circulate rated armature current through the short circuited armature terminals. Then measure E naught corresponding from OCC. So this E naught is obtained by IFT current. What is the IFT current? IFT is nothing but vector sum of IFA plus IFM. So see here. So it is an IFT current for lagging. IFM plus IFA sin pi whole square plus IFA cos pi whole square. Similarly leading. Similarly unity power factor. So once we find out this value by using this parallelogram, that value is projected from the x-axis to OCC curve. That will be again redrawn to this EOC line. That value will given as a no load voltage. So from that simply we are going to be evaluate voltage regulation of the alternator by using MMF method. So see here, the MMF method resultant field current is less than the actual value because of short circuited terminals. Therefore, the regulation in this case is less than the actual value, Hence, this method is called optimistic method. Next method, ZPF method. Again, same. What are the data required to obtain the voltage regulation by using ZPF method is OC test, SC test, and one more test is required, zero power factors test. And armature reactance test. So first see the here only ZPF test, zero power factors test. Zero power factors test means pure inductive load is connected to the armature terminals of the alternator. The circuit. Pure inductive load. pure inductive load is connected to the armature terminals of the alternator. That inductance value kept at minimum. Kept at minimum in the sense it acted as a short circuit. It acted as a short circuit means there will be, by adjusting the field current, still rated current through the flows through the armature terminals of the alternator. Now the inductance value is increases. The load inductance value increases from minimum value to maximum value, such a way that the field current is adjusted. Still rated current is maintained on the short armature terminals of the alternator. From that we are going to draw on the curve, ZPF curve, zero power factor characteristics curve. So that curve is nothing but here again it is an ZPF characteristics. ZPF characteristic drawn between field current versus open circuit load terminals of the alternator. So this curve is nothing but OCC characteristics. So see here, first draw the OCC, ZPF and air gap line on the same graph sheet. Initially we measured Vt equal to V rated. Draw a horizontal line to meet at point B. Then draw BC line. Draw BC line which is equal to OA. Which is equal to OA. Then draw CD line. This line. Draw CD line parallel to air gap line. Then draw a DH perpendicular to BC line. So see here, very easy in this this test. So first, what is the first one? First step, draw the OCC and ZPF and air gap line on same graph sheet. ZPF, OCC and air gap line. So then first line, at V equal to V rated, draw a horizontal line. Here measure V rated. Then draw a horizontal line. This is a horizontal line. Then from this horizontal line, measure, draw BC line. So this is the B and C points. This line, BC line. So how many centimeters we are going to draw, which is equal to OA. That is the point here. BC equal to OA. Once we draw the BC line, once of then next step after completion of this BC line, next draw CD line. How to draw CD line, which is parallel to air gap line. Simply we are from point C, we are going to draw CD line, which is parallel to air gap line. Then after make it is in a point which touches OCC curve, make it is in a point D. From point D, draw perpendicular line DH, which is perpendicular to BC. Draw DH line, which is perpendicular to BC. Then join BD. Then join BD. The DHB is in a portier triangle. DHB is nothing but as in a portier triangle. So see here. So what is meant by the DH? So DH is in a voltage drop due to leakage reactance. Voltage drop due to leakage reactance. So what is meant by the CH? CH is the field current which is required to compensate the voltage drop due to IAXL. Then what is meant by the BH? BH is a field current. BH is a field current to compensate the voltage drop due to armature reactance. So these are the main two field currents important. One is CH field current, another one is BH field current. CH field current. What is the use of what is the main requirement of CH field current? Which is this field current is required to compensate the voltage drop to leakage reactance. BH is the field current which is required to compensate the voltage drop due to armature reactance. So from that simply we are going to evaluate the voltage regulation. ER equal to V phase V cos pi plus IRA whole square plus V sin pi plus IAXS whole square. So from this we are going to be obtain the voltage regulation of the alternator E minus V by V. Next, Asm method. So simple method, in this method we are going to be considering a field current of A dash C. So Asm method, American Standard Association method. This method is simple method, same as before MMF method. What is the term we are going to be extra added in this method? A dash C is the field current which is required to overcome the drop due to saturation. Drop due to saturation. Same data here, just simply we are going to be added. This is the field current, that is nothing but A dash C. See here, EMF method is greater than ASA method. ASA is greater than ZPF. ZPF is greater than MM method, which is having high voltage regulation, which is having low voltage regulation. In middle, ZPF and AFA. This is the order of voltage regulation methods. Next, short circuit method. See here, short circuit value 0.6 to 0.9 for cylindrical pole type of alternator, 0.9 to 0.15 for silent pole type of alternator. Why? Because in air gap is more in between the rotor and stator. So for that short circuit ratio also more when we design the stable operation of synchronous generator. So next, these are the some gate point of view, small bit type of questions. What is the short circuit ratio of cylindrical rotor and silent pole rotor and synchronous condenser? Synchronous condenser is very small value, that is nothing but 0.4. What is the use of synchronous condenser is to improve the power factor of the alternator. Sorry, to improve the power factor of the electrical supply system. Next, see here, armature reaction, two reaction theory of an armature reaction. So already I told you that this two reaction theory only applicable for silent pole synchronous mission. This is not for as a cylindrical rotor synchronous mission. As before methods, that is nothing but EMF method, MMF method, ZPF method, yes, all these methods are applicable for only for cylindrical rotor synchronous generator. These methods are not suitable for silent pole synchronous generator. Why? Because in silent pole synchronous generator, already we are discussed, the air gap between the rotor and stator is non-uniform. Along the poles, minimum, in between the poles, maximum, such that the armature reaction is maximum along the D-axis, the armature reaction is minimum along the Q-axis. Further, we are going to draw an axis along the poles, that is nothing but direct axis. So in quadrature with poles, that is nothing but as a quadrature axis. There are two types of axes, quadrature axis and direct axis. In two reaction theory, simple. In this theory, to model the armature reactance, two reactances are required. One is direct axis reactance, another one is quadrature axis reactance, such that this theory we can call as a two reaction theory. See here, it is in a silent pole synchronous generator along the poles here. See, along the poles. So here air gap is minimum. Here air gap is here air gap is maximum. Here air gap is maximum. In this case, minimum. So minimum means automatically armature reaction in this case is maximum. In this case is minimum. Opposite. So here air gap is minimum. armature reaction is maximum. Here air gap is maximum, direct axis. So in between the poles, along the poles. So already here mentioned. See, Q axis. It is an D axis. So how we are going to be find out this quadrature axis reactance and direct axis reactances means by conducting slip test. Determination of XD and XQ by using slip test. So in this test, the field winding is open circuited. Field winding is open circuited, and armature terminals are connected to the three-phase supply by using three-phase auto transformer, and ammeter and voltmeter is connected, and voltmeter and ammeters are connected. So by applying reduced voltage, still rated currents are flows through the armature windings of the alternator. We are going to check that is nothing but voltmeter and ammeter values. So by conducting this test, automatically the ammeter is going to be oscillated and voltmeter also oscillated minimum and maximum values. Why this ammeter and voltmeters are oscillated minimum and maximum values in the sense? When armature MMF wave align with the direct axis, the current run is minimum. Why? Because the air gap is minimum. While the armature MMF is aligned with the quadrature axis, the air gap is maximum here. So align with, in this case here, the like this, here air gap is maximum. When aligned with like this, the air gap is minimum. So for that, here it requires minimum current, here it requires maximum current. When the rotor is runs less than the synchronous speed, at some particular instant, the armature MMF align with the armature MMF is aligned with the direct axis. Sometimes it align with the quadrature axis. When it aligns the direct axis, air gap is minimum, so that it draws minimum current. When it aligns the quadrature axis, air gap is maximum, then maximum current is drawn. Like that, the ammeter is going to be oscillating minimum and maximum. Similarly, voltmeter also. So for that, we are going to be write down as a formula here. Formula. So XD V equal to air formula. V max by I minimum. Similarly, XQ is equal to V minimum by I max. So once we find out XD, XQ values by using this slip test, so then automatically easily we are going to find out the voltage regulation of the alternator. So these are the methods to find out the voltage regulations of synchronous generator. In cylindrical rotor machine is different, and silent pole synchronous machine is different. In silent pole synchronous machine, by using two reaction theory, we are going to obtain the voltage regulation. Yes. So thank you, my dear students, those who are actively participated in this session. Now we are going to wind up the session. Thank you all of you, those who are actively participated in the session.